you will probably know that designing a secure system is difficult, right? That's why we're here, or at least that's why you're all here. That's why we exist, because people make mistakes when designing secure systems. So there's several challenges when you're building a secure system, and some of them I just summed up here more or less randomly. So performing hardware measurements to test security. It's difficult to do. It's what we specialize in, but it's something that we see and we also experience ourselves is difficult to do. You know, you get this hardware platform. Okay, so where do I start? How do I start measuring this or connecting to this? I don't know. I have to do this all over again every time. Designing and prototyping countermeasures, well, I don't know how many of you actually do that, but I would say that could be quite tricky to do, quite difficult to do. How do you test that? How do you test whether what you've made is secure? You don't want to go through the entire phase and create your hardware platform and then start testing, because then usually if you find problems, then you're already too late. And then the third one I want to tackle here is how do you educate new developers? This holds for us, also holds for you. You know, you get in new people. How do you get them up to speed? How do you get them up to speed on what security means, how you test this, how you talk about it? So the first challenge, measurement. This is usually me, like, what's going on here? So once you get a hardware platform, what do you do? How do you start? You require an oscilloscope. You know, where do I connect my oscilloscope? I have this little board here. Where do I connect it? What's the best place to measure? It requires a contact point to measure and to trigger. So maybe if I don't have a standard power supply, or my power supply is too far away from my target, I have to make cuts. I have to make additional contact points so I can measure. It's a lot of work. It introduces noise, of course, because we're living in the real world, no longer in simulation world. Wiring everything, well, just take a look at a few of the setups that we have in the other room. Wiring is always difficult to do. And if we tackle all of that and we get a measurement, okay, so now we have a measurement. Where is the leakage? If it's in there, how do I find it? They're all very difficult problems once you actually even get a proper measurement. Then challenge number 2, the prototyping. You know, if I want to start building a prototype for an SCA countermeasure, how do I test it? I don't want to run it through the entire process, build the hardware, and then start testing whether it works. I want to start testing early. And how do I decide whether this works or that works, or maybe I can join them? You want to have a quick turnaround on these kind of things. But you also want to test whether they work in a real life scenario. And then the third challenge, training. You know, how do I get my hands-on experience for myself, but also for new people? How do I teach that new staff how everything works? Well, the answer to all of this is, of course, measurement, but then hardware, scary. I'm going to do simulation. Okay, great. I'm going to do simulation of all the things that I built. How am I going to do this? Design time analysis. You know, we talked about this last year, I think. You know, I want to simulate everything that I've built, all the hardware that I've built. I want to simulate it and then build traces from that and analyze that. Great idea. In practice, maybe not so much. So the prototype design in the hardware space, you know, it's difficult. It requires a high expertise to make this entire layout and placing, routing. All of that requires expensive tools. It's slow. And even when you do get the whole simulation down, I think that from the tests I've seen, it takes like in the range of 20 minutes or something to make one trace. Okay, so usually for a proper test we need 1 million traces. That is not going to work. So it's very accurate, but for our purposes it's too slow. Okay, then we do software simulation. So we're going to do quick prototyping in C. You know, it's easy. Most of us have an idea of how to do it. It's fast, you just compile it and you load it. Great. But now I can't do the full verification of what I made, because I can only do partial simulation. I cannot simulate this entire board with all its peripherals. Maybe there's some hardware dependencies in here that I cannot simulate. So I can only do a partial verification of what I made and whether it actually works. Okay, so now I'm stuck. Now I can't do the software well enough, so I need to find something in between. So what we're going to do, and what I'm going to talk about, is doing software simulation on the hardware. So it's basically the best we can do to get all of the requirements in that we had. Now, how do we do this? Well, I showed you the little board. This is a little example that we made. One of our employees made this. He called it Risca Sim. It's built on the RHME3 challenge board that we used last year for the RHME challenge. It's a very simple board. It's Arduino-like, and it's well documented, so we know a lot about this. So great. Now we want to collect traces on this thing, because I just built something. How do I get traces with this? Because, you know, I don't have an oscilloscope here, and I don't want to go through the trouble of wiring. So I have my target, but now I want some measurement equipment and some trigger. Okay, so how do I measure without equipment? Well, DPA attacks, they use a leakage model to represent reality. Usually the leakage model that we use is, you know, CMOS. It only consumes power when it's switching. Right? If for those of you who've done the basic training or have some basic SCA knowledge, or DPA knowledge, this is how we simulate or basically model what happens in the actual chip. Okay, so can we simulate that somehow? Well, we could. We could leak the register values in the chip, and we get a perfect leakage, right? Because we have the actual value in there. But now, of course, we have some other constraint or some other problem. You know, how often can we sample that? Well, it's great because for us, for this, we developed this little board. We can do some instrumentation on the chip. Probably for the developers among you, you have the same thing. You can halt the chip after every instruction because you have the tools to do that. Okay, so we can do some instrumentation. Instrumentation, generally difficult. Now it's complex to do, it's not really feasible in this AVR microcontroller. I could do it, but it's more difficult than what I want to do. I want to make something simple. I can do compile time translation, nice, but then my program goes from here to, it's a giant program that I don't have to load on this target. I also don't want to do that. So what I'm stuck with, interrupts. Well, then you do a little investigation into this target, and you find that this thing actually supports some interrupt service routines. So that means now we can leak an arbitrary register value after every instruction. That's great. So now we can sort of build a white box on our little target. So what happens? Well, we build some leakage models. We want to simulate CMOS in this case, so we have some Hamming distance, some Hamming weight that we simulate. How do we do this? We just take the register value, we calculate it in the instrumentation. and we send it back. We just pump it through the UART. But of course we can leak anything we want. So we can leak the program counter, we can leak the white box, so all the values of all the registers, whatever we want. And then we get something like this. Well, anyone wants to venture a guess what we're looking at? 1, 2, 3, 4, 5, 6, 7, 8, 9 and a bit. So I'm going to guess AES. I have no prior knowledge whatsoever, of course. So, then we have one other challenge. How do we trigger? Well, actually this is not a challenge at all anymore. Because if we want to start measuring, we enable the interrupts, and as soon as we enable the interrupts, we trigger, we start measuring. So the triggering problem is also down. So now, we have everything we want actually inside the single board. Well, now let me show you what it actually looks like. Just quickly here. You can't see this, but now you can. So, I have some instrumentation file here that is loaded onto the board when I'm compiling. And what I do here, you create forever after every instruction, this thing runs and it creates the Hamming distance and the Hamming weight of whatever registers it reads, but it's basically all of them. And then it just throws this through the UART. So what do I get then? I get a simulated trace, perfect leakage, without any measurement, any actual measurement. So so for instance here we have an AES, a very simple C program. It just does, for those of you who know AES, this is the most basic implementation we have. It does nothing special, it just does AES. So what I can do, let's see, you can probably also not see this. So we have, So we have several challenges here that we built. And what I can do is I can just flash this to the board. Let's flash the stock challenge. Okay, so it just writes whatever I just wrote to the board, split second. And then I have my control program. So now what I'm going to do is I'm going to run my client on my COM port here. I want to output TRS. Great, because then I can load it in Inspector later. I'm going to leak the Hamming distance. In this case, the Hamming distance between two consecutive instructions, which is not optimal for me. Usually I want the Hamming distance between before and after an operation and not necessarily between instructions, but for this model it will do fine. I'm going to save that trace somewhere. I'm going to run 100 acquisitions. So I'm going to run 100 AES encryptions through this board. There we go. It takes a little while, but then you can see the input and the output here, and you can see the size of the trace that we created. So we created 11,000 sample trace that has the Hamming distances between a register and its next state for every register. Okay, so we create this, and then, well, in a second I will actually show you what it looks like. But this is just a quick rundown, a very quick rundown of the system that we have running here. Basically, well, I will show you. I will show this platform in the next coffee break as well. So if you want to check it, just drop by, and I can make some changes to the code quickly, and see what impact it has on the trace. Because now this took me 1 minute, maybe, to change everything and to run the simulation again. and I'll have a trace. I'll show you in a second. So, we can now make traces from our target operation. Okay, and what do we need now? We need an operation to target. Well, as I just showed you, I implemented AES on this thing, but I could implement anything that could run on this board. Now, we need some way to attack these traces. You can use anything. Actually, for the demo that my colleague made for this, he used an open source platform to attack this. In my case, I'm experienced with Inspector, so I prefer using that. So, I'm just going to show you a quick comparison of 3 cases. So the AES-stock, this is what comes out. So if I run that, I open it in Inspector, which I'll also show you. This is what you get out. So we can still actually recognize the rounds, at least, if you have a bit of experience. It doesn't look amazing, it looks a bit flat, but it's great because it's simulation. So it leaks completely. There's no noise whatsoever, unless I add it, of course. Then I have a jitter implementation that just adds a bit of jitter to make it more difficult for an attacker. And then I have a third one that actually has dummy rounds. So now we see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 rounds. So am I now dealing with AES 192, or do I have some other weird stuff going on? Well, actually, if you look at it, we can analyze it. So this was the stock one I just showed you. It's very easy to break, which I'll also show you with Inspector. Now the next one has a bit of jitter. It's just, I put a countermeasure in. It starts with a random number of knobs. Just adds misalignment, which makes it more difficult for the attacker. But still, we can break this, of course, by doing static alignment and attacking from the output or from the input. It actually doesn't really matter. Then with the dummy rounds, now I'm going to do something slightly more sophisticated. So I'm going to add some dummy rounds at the start and some dummy rounds at the end, a random number of them. So now I don't know where my AES is going to be. How do I break this? Well, in this case, I broke it. This was something that my colleague made, and I broke it by, okay, so I can see a random number of dummy rounds. Sometimes that random number is 1. Well, if there's only 1, that means that it's always going to be at the start. Therefore, I just reject everything that's longer than 11 or than 10 rounds or 11 rounds, visible rounds. And then I have only traces that are okay. So how would I implement it properly so that it makes it very difficult for myself to break? So in this case, you can be in a split second, you can be attacker and defender at the same time. And you can challenge yourself to break your new countermeasure, or maybe one of your colleagues, just for fun. Okay, so I'll show you what it looks like in Inspector. So, for instance here, so this is our, again, you can't see that, of course. There. So, we have our stock implementation. Let's see if I can move this thing a bit. So this is the normal AES we have. If I zoom in a bit, it may be easier to see. We have, well, still difficult, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rounds. Great. Well, I have 100 traces, but I also don't have any noise. Let's see if I can break this. Yes, then of course this also pops up on this screen. So what I'm going to run AES output to input. Sure, let's see if that works. I'm going to run it on the whole trace because I'm lazy, I don't want to select anything. Okay, good. Okay, so it found the key. just like that. No measurement equipment whatsoever, but I can still use all the peripherals and all the data that's, or all the hardware that's actually present on the chip. Huh, pretty nice. Well then, let's attack the jitter one. So we can scroll through the traces, we can see that there's no alignment anymore. So if I run it on this one, I can guarantee you this is going to fail. Let's see if it's actually true. You know, demo effect, suddenly I get the key for free. Nah, no such luck. All right, well then let's see if we can be smarter than my super intelligent countermeasure. Let's say I want to align. Well, I see here that this looks like the jitter that I introduced. Great, then let's see if I can align on this pattern here. Oh, and then of course that all disappears that way. Well, it doesn't really matter either way. Let's see if I can do some alignment. Ah, it made it a bit weird, so I guess that's not a very good alignment. Let's see, how many samples did I select? 600. Well, let's not shift this much then. Let's do a maximum of 1000, see where we end up. Okay, great. So now we have some alignment. It looks, it doesn't look great, to be honest. I can do better. Well, one more attempt and then I'll stop bothering you with this. Okay, so now I have 85 traces, but probably they are aligned. So they're aligned at the output now. Okay, well then let's see if I can make this work with 85 traces. Nope, it's there again. Ah, well, it doesn't seem so. It seems that, oh, yep, it found the key. Okay, so it did find the key. So now I broke my own countermeasure. Pretty fun. Now, of course, I can keep going and make even more difficult ones, but let's save that for the demo later on. You can make your own countermeasures, have me break them. Why not? Where's my mouse? There. All right, so let's just revisit the challenges that we posed at the start. You know, hardware measurement, difficult to do. In this case, we can simulate the leakage, and it provides a very easy alternative and with a quick turnaround. We can quickly judge the effectiveness of our countermeasure, because we don't have to wait for the entire chip to get, you know, fully prepared. No, we can just flash our new countermeasure, see what influence it has on our perfect leakage. Of course, if I can break something with perfect leakage, it doesn't really say that it's still breakable if I measure it from the outside, but it gives you a baseline on how difficult it is to break your countermeasure. And I can use this for training. I can use it to educate new people. You know, what do you do? What don't you do? How effective can this be in real life? So, as your takeaways, the thing is, I'm not trying to sell anything. We just built this thing on a little board. We're not going to sell this, this platform to you, but it would be fairly easy to make if you're a straightforward way of thinking about leakage. Look, I have all these registers, I compound them into a value, and that I send back to my PC. And it's a system that's easy to implement on different platforms. I mean, easy, relatively easy, of course, depending on your experience, but it gives you a fairly straightforward platform to test what you're doing. Yeah, so if you want to do it yourself, just come visit me in the other room. You can maybe put some code changes, flash it, see what it does to the trace, see if you can still attack it yourself. And just as an accreditation here, this was not developed by me. It was developed by Kevin Valk, who is one of Risca's employees. I just want to mention his name. If you want to know more about the platform itself, and you can take a look here. This explains about the platform, also how to use it, how to use the system itself. If you have one of these RHME boards, which some of you may, you can actually build the platform yourself and start playing with it.